Hello everyone, welcome to today's webinar. I'm Linda Wang, Senior Editor at Chemical and Engineering News, and I will be moderating today's event. This webinar is titled An Overview of High Spatial Resolution Detection Solution using the latest sCMOS and Scintillator technology and is being sponsored by Andor and co-hosted by Carter. CNN works with sponsors to identify topics of interest and value to CNN's audience and consistent with CNN's mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please look at the Help widget at the bottom of the screen or type your query into the Q&A box. If you are disconnected during the webcast, please log in again according to the instructions you received earlier. You are encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. The questions will be answered at the end of the presentation, and as your moderator, I will be posing as many as time permits. Please note that CNN does not endorse any company products or services that may be mentioned in the webinars, and that each webinar will be archived at CNN Online after the live webcast. Today's presentation is sponsored by Andor and co-hosted by Carter. Andor is a global leader in the pioneering and manufacturing of high-performance scientific imaging cameras, spectroscopy solutions, and microscopy systems for research and OEM markets. Carter is one of the world's leading companies in synthetic crystal manufacturing and processing, with a strong focus on niche applications and client-specific projects built on high expertise and close cooperation in research and development. During the presentation, we will hear from Colin Duncan, application scientist for physical sciences imaging at Andor, and Jerry Pierzek, technology application specialist at Carter. Colin studied physics at Queen's University, Belfast. During his time with Andor Technology, he has worked in a variety of roles, gaining a high level of technical expertise in the area of CCD cameras and astronomical imaging. Jerry studied physics at Charles University in Prague. His interests lie in optics and optoelectronics, including special applications such as X-ray imaging systems. During his time with Carter, he has participated in projects related to photon counting imaging devices and use of scintillators as imaging screens. I will now hand the presentation over to Jerry.
Well, thank you very much. So let's begin with the presentation. I think that everybody knows X-rays from its own experience with doctors when you had some accident and you felt pain in your leg or arm. So you went to the doctor to see if something had happened to your body. So X-rays are penetrative radiation, which were discovered in 1895 and have high energy that starts at 10 electrovolts to 100 keV. Well, the basic operation with X-rays will be radiography. It's imaging of sample structure using radiation. Because they are highly penetrative, you can see actually the composition of the material, the defects, and everything, what's hidden to your eyes. There are different configurations. First of all, we can have absorption radiography, which is the way how the doctor actually performs his scan. You have a point-like X-ray source which irradiates the objects, and then there's an imaging detector in a certain distance behind the detector, and you can image it on an imaging detector. This is the first variant. The second one would be isotopic marker. Then you have a marker here. You put something to patient's body, for example, and you are able to measure the radiation which comes from the marker. The third option would be X-ray fluorescence, when you irradiate the surface of some material and you measure the X-ray radiation, the fluorescence, which comes from the surface. So radiography is very helpful to many people in the world to see the structure of the material. So let's talk about detectors. So we have many detectors for radiography. The oldest one would be film emulsions, which provide very high resolution. They are very cheap and have very low noise. But on the other hand, they exhibit a nonlinear response and limited dynamic range. And also you need some processing to see the image. It's the old way. For now, we have different methods which are more sophisticated. The first method would be scintillator and charge integration detectors, such as a CCD camera, CMOS camera coupled to a scintillator. And this would provide high spatial resolution, also for low price, but some disadvantages would be dark current and noise and limited dynamic range. The third option would be photon counted detectors, which also Kritur has in stock. He's interested in new technology, so scintillators and photon counting are the future. And here there's a good spatial resolution, which is lower than with scintillators, but there is no noise, no dark current. But unfortunately, the price is very high for now. So let's move to scintillators. What's a scintillator? Scintillator is a method that can detect X-rays or high-energy ionizing radiation by material. Scintillator has intrinsic properties of luminescence, so if you radiate the surface of scintillator, the energy is converted into photons that are in visible range of the spectrum, and then can be detected by, let's say, CCD or CMOS camera. There are different types of scintillators, and also they have different characteristics. We are going to talk about single crystal scintillators today, but for imaging, we would also speak about LPE scintillators, liquid phase epitaxy scintillators, and powder scintillators. Unfortunately, these two are quite demanding to process. For LPEs, there are some defects which have a deteriorating effect on the image, and powders, they have grain size which actually scatter the light to worsen the resolution of the system. So what are some key factors of the scintillators? Well, first of all, it's conversion efficiency, which exactly tells us how much radiation is converted to the visible light. The property is called light yield, and we can speak about several photons per 1 keV radiation. The other parameter is absorption, which strongly depends on the atomic number of the material of a scintillator, and tells us how much radiation is absorbed and thus converted to the visible light spectra. Second key factor will be X-ray stopping power, which is connected to the length, how much thickness of scintillators you need to stop the X-ray radiation from transmission. For imaging, we have to speak about luminescence decay time, which is about several nanoseconds, and also afterglow, which have some effect on the signal. The luminescence decay must be lower than the rate of the integration of the camera, but it's usually okay. For the afterglow, there might be some problem, because if the afterglow is high, it creates residual light and it diminishes the picture. Spectral matching is something you need for spectral matching with the camera, because it's great that scintillators that we usually use are connected to CCD, which has its maximum at 500 to 600 nanometers, which are greatly coupled with the quantum efficiency of the sensor. There are also other properties such as chemical stability, which is hygroscopicity, and then spatial resolution. This is what we are actually going to talk about at the end. So there's a list of several applications that you might be familiar with, such as network applications, high energy physics, security check, non-destructive analysis, good checks, and other applications, which actually tells us where scintillators are used and employed for some functions. So So you can see that scintillators are basically almost everywhere around us. So what are some materials that exhibit scintillation? Well, today we are going to speak about garnet crystals such as YAC, which is doped with cerium, and also LUAC, which is doped with cerium. And we can see that its emission wavelength is about 550 millimeters, which is great for coupling it with a CCD. Also, they are non-hygroscopic, so they are very chemically stable. Their photon yield is about 20 to 30 photons per keV, and decay time is pretty low for imaging. There are different types of scintillators, as you can see from the table, but you can see that the emission wavelength is usually somewhere to the UV part of the spectra, which is not good for CCDs or CMOS coupling. And also the hygroscopicity of some materials, such as cesium iodide, for example. So let's see LUAC and YAG. So these are these yellow scintillators, or the scintillation emission wavelength is in the yellowish and greenish part of spectra. What are these? What are their common features? First of all, they are single crystals, so it means that if you manufacture a very thin screen, they provide very high resolution imaging because there is no scattering inside. They have a great match, spectral match with a CCD, short decay times, thermal stability, which is great because if you need to use in vacuum or something like that, you need to get the heat from the scintillator, so the heat will not stay in the scintillator. They are chemically stable, so they are non-hygroscopic, and also their radiation hardness is 10 power to 14 Grays, which is very high. These can be manufactured actually on different configurations, such as a fiber optic plate, or they can be fixed in a frame. So these scintillators can then be coupled by various ways to a detector. Let's switch to the next slide to see what some future outlook can be. So we are constantly looking for finding new scintillators, especially ultra-thin screens, which would provide very high resolution. This resolution can be really very high, even below 1 micron. Then high efficiency, this is connected with the light yield, so we need to get more photons out of scintillators to have higher signal on our detector. Higher stopping power is something which is very interesting for high radiation, and also lower decay and afterglow, because afterglow, as I said, is connected to the residual radiation, and it will have a diminishing effect on the image quality. So actually, what can we actually do to avoid this process defect? We can have pure materials, which is always the question, or we can dope them with different materials that will prevent it from radiation. So we are actually searching for new materials that can be made down to ultra-thin screens, and this is something which is very demanding. We need a lot of background, a lot of research, but we believe it can be done to provide the best resolution in imaging. At the end, I would like to ask a question. Have you ever heard or have you ever used scintillating screens by cryo? The answers, the options are yes or no, and you have 30 seconds to answer. And I would like to also encourage you to ask questions at the end of the presentation. If you have anything on mind that requires our attention, we'll be happy to give you some answer, and we can maybe discuss in details in the future. So I hope that everybody has had enough time to answer. So let's hear the results. So as you can see, there's a lot of people attending the conference which are not familiar with Creator, which is quite sad for everybody, because I think that our screens are great for imaging, and I will give it a try, and you'll see. So thank you for answering the questions, and I'll give a word to Colin to continue with the presentation.
Sorry about that, bit of a sound flaw. Thanks very much, Yuri, for the overview and the background on scintillator and future technology. Where we're going now is actually to look at the back end, the detector solutions. Specifically, we'll be looking at the Zyla 5.5 HF, which is based upon a new technology that's coming to the market, which is the scientific CMOS. So a lot of people will be aware of what a CMOS camera is, the scientific CMOS is a little bit different, and it's brought new capabilities into this market. So we also make a range of other cameras, and we'll go into the next screen and we'll talk about how they apply and the kind of market we see. The first thing to show here, obviously, is here's a picture of the camera, but more importantly, showing the definition and the quality of image that's attainable using the detection, so the high spatial detection available. So when we make cameras, and we make a wide range of high-end scientific cameras, normally we produce CCD and sCMOS cameras for what we describe as a higher energy detection. And by higher energy, we're just simply talking about energies above the visible. And as Yuri covered earlier, that's looking at anything from 10 eV up to 100 kV. What we're trying to indicate with this graph is the kind of spread of energies that can be seen. With the green, we're indicating a direct detection, and then clearly later on, you can see the scintillator coming into play more. So Yuri has a very good presentation at the end, and he'll be showing the joining together of a scintillator technology with the detector technology. So the graph here is to give you indication. The green is showing what a standard CCD will do, and the blue on the top of the graph is representing where the scintillator starts coming into play. So it's just to give you a kind of broad feel for how and where those technologies are coming into play. So if we go on to the next graph, let's deal directly with the CCD sCMOS description and see how we can identify the difference and why the sCMOS is bringing a new ability into this market. So if I seem to have paused slightly. Hopefully we can move on to slide 14. That seems to have lagged in my. So in slide 14, what we're trying to show is what the scientific CMOS is bringing. It's bringing a unique capability. If you look at a CCD structure, you have effectively limitations where you can maybe choose a fast readout, but you'd have to have a small effective field of view. Or you could go for a wide dynamic range, but you'd lose resolution. What the scientific CMOS brings is a different structure it brings the ability to have all of these key aspects of a detector in one camera. So here you can see the effects of that. If we look at the list, we have extremely low noise down to 1 electron, rapid frame rates up to 100 frames per second of the full frame, a wide dynamic range. Now, effectively, this is electrons before we get the scintillator, but it's a very effective way of moving the charge of up to 33,000 to 1. High resolution, which is obviously critical, as we'll go into and Yuri will explore later on, with a large field of view of 5.5 megapixels. It's able to do that because it's a different structure. So if you look at the diagram on the top right, what you should see is effectively a charge entering at the same time, so a higher energy photon going into either the CMOS structure or the CCD structure is moved differently. And this difference in how the transportation of the charge happens allows you to have this difference in performance. So by having this different performance structure, we can get this better performance. So if I look at the CCD, the charge enters into the pixel and then is effectively clocked down and then out along the surface. So it takes that individual photon a long time to move through the clock down and along. And that is the effective frame rate. So most CCDs are working in the regime of 4 or 5 frames per second. If we move to the CMOS structure, it enters into effectively the pixel, but then can be read out through a buried channel immediately. So you no longer have to clock the charge all the way through the surface of the sensor, but you're able to bring it in and move it. So that is a CMOS structure. So what is a scientific CMOS? All scientific CMOS brings is the effective linearity of response for the CCD-like qualities to a CMOS structure. So what we've developed is effectively a CCD performance in a CMOS structure. So that gives us all of the advantage of fast clocking and the large field of view, which we then want to maximize. So if we move to the next slide, we find we need to deal with how do we get the light from the scintillator or from the matter you're looking at into the camera. So we have to make sure we have a highly efficient, high resolution throughput. And we do this by focusing on our optical design. And we do that by ensuring we have a high throughput. We choose fibers with a direct coupling, so that means there's only a single fiber. It's got a high 80-20 core ratio. It's maximizing the light throughput. It's minimizing the crosstalk. So crosstalk is stray light or light that's not where you want it to be, and it's done through a EMA, Optical Design. And we also have a resolution on the fiber, 128 line pairs per millimeter, using a 3-micron channel fiber design. This is all with obviously zero gross or shear distortion. So when we're talking about that, what we're talking about is effectively ensuring that the image is not corrupted by being spatially moved or displaced. So all of that leads to a high throughput, high resolution system. We then move to what does that mean for the final detector that is put behind the scintillator? Well, it means then we have a high frame rate, large field of view. So here we're talking 16 by 14 millimeters. We can also expand this by putting a higher taper on. We have the single fiber design. We have high spatial resolution. We have the low read noise. And then we move on to the capabilities we want to bring on top of that. So we've developed a detector which is running fast. It's efficient at the transfer of the light, but we also need to bring more to that because what we want it to be is a flexible tool. So we use a modular scintillator coupling. So when we look at the actual optical performance of the camera, this before we put or couple anything on, we can show that we have a nice, efficient, and effective design. We do this simply by looking at a USAF 1951 target. And here you can see all we're doing is we're looking at the resolving power test target, which I'm sure a lot of you are familiar with. And we're able to focus into the central region, and the cutout in the right is effectively looking at the central region where we're able then to do measurement of the line pairs per millimeter. And as you can see, you're still getting fairly good definition down to these levels. So all this is about is creating an efficient transfer mechanism for the light that is being generated in the scintillator. So we're trying to match the efficiency and spatial resolution of the camera with the high quality scintillators that are being supplied by Crytor. So we don't want to effectively be limiting the efficiency and resolution of the system. So that's fairly straightforward. What we then do to give the customer the ability and the tool to their hand of modulating or correcting. If someone could move to slide 18. What we've done is we've created a modular front end. So the design is to enable at the user end the ability to swap out scintillators or beryllium windows. When would you want to do that? Well, theory I think we'll cover it to some extent. It just is when you're going to change energies, or you want to change the effective resolutions to throughput. So you've got the ability at the point of use to change the camera. As you can see, it's a fairly straightforward system. Obviously, the beryllium window on the front is to act as a light shield to remove visible light and allow a capture of the desired energies or higher energies. So all we're doing is delivering that capability of the camera to the user. So it's about flexibility from the user point of view, and it's a key aspect of all of Andor's camera designs. So if before I finish up, I just say this is a brief overview, and we're just trying to cover some of the aspects of a specific product of Andor. If you look or want more information, please feel free to go to Andor's website, specifically Learning Academy, or any of the other information. You'll find there's quite a lot of information that you can peruse at your leisure. So to finish off, what I would like to do is ask another question, following on from Yuri, just to get a feel for where you sit, is if we could put the poll question up. We're just, it's an interesting conversation from our point of view. What is more important to you? Would it be high resolution? Should we be looking to improve resolution? Or is it high throughput for an indirect detector? So something that's using scintillators to convert into the detector system, as we see. You know, we're just getting a feel. What do you feel would be more important? High resolution, high throughput. And the same thing as Yuri said, if we could take 30 seconds to have a think about it, and we'll just try and gather that information. So it's trying to make it a bit binary, but hopefully there's some strong preferences, and we'll see where the majority of you feel the improvement would lie. Okay, so high resolution, which, considering the title of the presentation, should not be too much of a surprise. Okay, so now we've talked about scintillators and we talked about the camera. I'd like to hand back to Yuri, and we'll see kind of some real-world work that's been done using our detector and the scintillators from Crytor. If I could pass to you, Yuri.
Thank you, Colin, for the presentation. So Colin had a great presentation about Zyla, which has fiber optic input, and we had an honor to actually test it with our scintillators to see what the spatial resolution would be. So first of all, we have to speak about the spatial resolution, what it actually is. So the spatial resolution is the ability to resolve or discern details of certain size in the image. So on the left-hand side, you can see a picture how it actually works. If you have two small particles, for example, lines, if they are too close together, they would not be resolved due to the optical system transmission, because if the object if you have the object which has 100% contrast, the optical system will not transmit the contrast. So we can actually speak about two factors, the resolution in micrometers, but also we have to speak about contrast. We need certain contrast to see the details in the image. What are some limiting factors? So first of all, it's the optics. We have different coupling of a scintillator to a camera, and the optics will have certain effect on the image. Then also, we have to speak about a scintillator. There are effects such as the thickness of a scintillator, for example, that will have effect on the image, as you will see. And also, the detector plays its role in the imaging because it has a certain pixel size which is defined. So it will actually define the smallest point of the image you can see. Then there's different factors such as noise, etc. So the units are usually line pairs per millimeters. So you need some line pairs which is black and white paired together, and the number of line pairs per millimeter which tell you what the resolution of the system is. You can also use different units such as microns, which is in the spatial domain, which we are actually used to. So let's see what's the best characterization of the optical system. We spoke about resolution and contrast. So we need to put these two together. So if you use so-called modular transfer function, MTF, where it's a graph where on the x-axis we have spatial frequency in line pairs per millimeters, such as in the number of these pairs per millimeters, and the y-axis contrast in percent, we can actually say how good the system is. We are usually aiming at contrast about 10%, which is somewhat sufficient to see the details in the image. So how to measure MTF practically? Well, there are two ways. As Colin pointed out, there are certain patterns. It's USAF for visible light, but for X-ray we need GIMA X-ray test chart, which has a clear number of pairs which will be imaged by the system, and by seeing the image and getting the parameters of the image, we can see how many actually line pairs will be visible in the image. Or the other option would be indirect measurement, which is usually conducted by slanted edge technique, which is very popular, and also it has been used with cameras, with scanners, with almost all imaging devices. So let's see what the slanted edge technique is about. Well, it's actually characterized or defined by ISO 12233. It's about electronic still picture imaging, and it tells us how to measure the MTF of the system. So we need a slanted edge target image. We need to image it and then do some processing on the signal, where the implementation could be done in MATLAB, such as a script by Dr. Burns, who developed a script that is able to count line pairs per millimeter from the image. So by imagining the slant edge, we actually derive edge spread function. We take derivative to have line spread function, and then by Fourier transfer we have modular function, which is the final verdict on the system. So let's talk about experimental setup we actually used. We used the slanted edge technique, as I said, with an X-ray works tube which has operational voltage between 20 to 160 kV. There are optional anodes. They can be copper, molybdenum, or tungsten. and the power on the target can be about 10 watts. This yields to spot size, or the best spot size would be below 1 microns, which is actually good for imaging because the finite spot size will affect the resolution of the system. So a very small spot size is great for imaging, and it can be done. And this system provides for chromatic cone beam. So if you put a sample somewhere between the detector and the X-ray source, it will be magnified. So you need to avoid this magnification by putting the edge on top of an imaging screen, which is coupled by fiber optics to Zyla HF. For a slanted edge, we use a molybdenum edge of 50 microns, and we tested different scintillators in a range from 30 microns to 500 microns or 200 microns. These were freestanding scintillators, but we also had a chance to test a scintillator which is glued to fiber optics, which will be coupled to another fiber optic input of the Zyla. After we measured these images, we need to do some processing, which would be background and flash field correction, and then the processing in MATLAB to get the MTF of the system. So let's see. There are some preliminary results. So on the left-hand side, you can see the slanted edge, the image, and the variation of the contrast, the edge spread function, which can be easily get from the image. On the right-hand side, you can see line spread function, which is the derivative of the edge spread function, and actually its thickness, or the SVHM, will tell you what the resolution of the system is. So, for example, this one was measured on a sample of LUAG of 30 microns with X-ray radiation at 40 keV on copper target. So we actually use the branch traveling and K-alpha of copper. And it was integrated by Andor Zyla for 5 seconds. So by taking the Fourier transformation of the line spread function, as I said, we received the result, which is the spatial frequency response. So on the x-axis is the spatial frequency, and on the y-axis is the contrast, as I pointed out. So 1 means 100% of contrast, and we actually use the 10% value, which is resolution about 39 line pairs per millimeters, where the actually cut-in frequency would be somewhere like if the system would be if the system were without defects, and the optics could transfer everything, would be the Nyquist frequency. So you can compare our spatial frequency, what we obtained, to the Nyquist frequency, which would be a sampling frequency of the detector. So it's 39 line pairs per millimeters. So what about the other scintillators? Okay, let's see. We have a graph, and it actually shows the relation between resolution and line pairs per millimeters to thickness, which is not a good evaluation for us because it will be reciprocal. Value 1 over resolution is better, so we can speak about line pair width in microns, and we can see actually that the line pair width is linear related to the thickness. If we speak about scintillators between 30 to 200 microns, so there's a linear dependency. Let's see some sample pictures, what we actually got. So this is an image made by X-ray radiation of 70 keV with a tungsten target with 2-watt power on the target, and by Zyla. So this is a comparison between resolution of two different thicknesses of scintillators. On the left side, we can see 550 micron YAG on FOP, and it's clearly visible. It's not blurred actually. You can see 50% of the original image. But on the other hand, if you switch to a thicker scintillator, you get a worse resolution. I'll get back to the slide. Let's see. The 50 micron scintillator on FOP would have line pair width about 30. There's that green point in the graph below the red line, and that 200 micron thick scintillator would be about 160 micrometers when we speak about line width, which is equivalent to 6.3 line pairs per millimeter. So you can see a clear difference here in the graph, and what actually corresponds to the image quality. What would you expect from imaging? So let's get back to the WASP. So it's here. So you can see it's clearly better. So if you use a thin scintillator, you will have better spatial resolution. So let's go to a summary here. So first of all, what we actually measured with Zyla is that the line pair width in the resolution microns is proportional to the thickness of the scintillators. So it means if you have a scintillator of, let's say, 100 micron, you can expect resolution in line pairs in the thickness of these two line pairs, or the thickness of these two lines of the line pair of about 100 microns with YAG or LUAC. The highest resolution achieved was over 33 line pairs per millimeters, which is better than 30 microns, and it's the same as Colin showed in the graph that Zyla has resolution over 33 LP to millimeter. So it actually tells us that the scintillator, if it's very thin, is not a limitation of the system. It has some effect, but it will not deteriorate the resolution that much if the screen is very thin. There were two lines, so we could see that YAG, let's see, it will be easier for you, is slightly better. So YAG is the red line, so you can see that it's lower in the graph, so it means you have more line pairs per millimeters from YAG. But we actually have to confirm that we use polychromatic radiation, so it means that it's absorbed in different thicknesses. So by this, LUAC is actually favored by higher integral conversion efficiency for energies over 20 keV, which is due to the polychromatic X-ray source. Thus, you will have a higher signal on the image. And also, we actually confirmed that the X-ray spot is small enough to maintain resolution between 20 to 100 keV. As I said, the X-ray spot was about 1 micron, and that's it. The resolution is more than 1 micron of the system, so it means that the X-ray spot didn't play any role in that. So, thank you. Thank you for having this presentation, and I will switch to Linda.
Thank you, Jerry and Colin, for your terrific presentation. Now begins the Q&A portion of this webinar. The first question I have here is the fiber optic permanently coupled to the sCMOS sensor?
Sorry, yes, I can probably answer that one. Yes, the fiber is currently bonded to the sensor, but we have actually got modules and capability of putting other fibers on, but the camera has got direct bonded, so yes.
Colin, I had a little trouble hearing what you were saying. I think that the connection was not good. I was wondering if you wouldn't mind repeating it, just in case others
no problem.
Couldn't hear the answer.
Sorry, the fiber is directly bonded onto the sensor, and that is a permanent bond. We offer other fibers on top, so you're able to effectively have another fiber you can apply onto that. But the camera core is bonded and is a permanent bond.
Well, may I add something?
Yes, please.
Okay, so you can actually couple the scintillator just by pressing it on the top of the fiber optics of the camera with using some liquid or something like that, or you can use a fiber optic plate glued to a scintillator and then press it against the fiber optic input. So we actually confirmed that if it's these two options, we actually give you the same resolution. The FOP, which is added to the system, will actually not have effect that is measurable to the resolution of the system.
Okay, thank you. Another question I have here is it possible to image an object larger than the scintillator, given that you can't focus X-rays?
Well, actually, it's a good question. The scintillator actually works as an imaging plate. So the object must be smaller than the scintillator itself, or it must be measured by some parts. If the object is bigger than the scintillator, you need to do some small images and then put it to a bigger image at the end. It's actually not possible. So the answer would be the object must be smaller, or you need to do some partial imaging.
Okay, great. Thank you. What solutions do you suggest to couple scintillators and camera detectors together?
Well, there are basically, let's say, two solutions. The first one would be using microscope objectives to couple the scintillator to CCD camera, or the second would be using FOP, as we are talking about it today. So we can put it on top of the FOP and directly image it on scintillator, use FOP to guide the light to the sensor.
Okay, thank you. What are typical thicknesses of the high-resolution scintillators?
Well, actually, it's an intricate question. It's a tricky question. We can start, let's say, from 5 microns of thickness for Yak and Luak to, say, 100 microns for imaging, or millimeters, but it has an effect on the resolution. For the greatest resolution, you need as thin scintillator as you can, so 5 microns would be the best. But on the other hand, if the scintillator plate is not thick enough, it will not absorb all the radiation, so you will lose the signal. So you have to think about signal-to-noise ratio and balance the thickness of the scintillator and the absorption of the scintillator to get the best result. And it depends on the application, which are actually different.
Okay, thank you. Can scintillators be coupled to systems that operate at temperatures above 80 degrees Celsius?
80 degrees Celsius?
Mm-hmm.
Well, actually, scintillators, our scintillators, garnets, are very stable with the temperature. So 80 degrees and the input would not be a problem. The melting point would be somewhere 2,000 degrees, so 80 degrees will work with the scintillator.
Okay, thanks. Do you have scintillators for detecting thermal neutrons?
Well, for let's say for thermal neutrons, you need a layer which will convert the neutron radiation to alpha particles. It could be some lithium fluoride, for example, a very thin layer of lithium fluoride on top of scintillators. So the neutron is converted to alpha particles, which are then converted to visible light and thus visible on the CCD.
Okay. Thanks. Do you lose light when you press a scintillator fiber plate to the fiber on the camera?
I'm sorry, I didn't hear the question.
Do you lose light when you press the scintillator fiber plate to the fiber on the camera?
Well, I think Colin wanted to add something.
Yeah, sorry. I mean, it's a good question again because with the scintillator, you don't really, because I think you're collecting. You do have the danger of two optical surfaces, so you have light being lost. If you get a mismatch between fiber plates, then you can get effectively a loss there. But I think as Yuri covered in his report on the testing, they actually did use scintillator fiber onto the plate and didn't see a loss. It maintained the resolution. You may get a slight loss in the throughput. This is one of the reasons why we specifically design a few fibers, so we have as few surfaces as possible, because one of the aspects is to make sure we don't compromise throughput. I don't know if you want to add on to it.
Okay. Thanks. What type of cooling does the camera use?
The camera is effectively a Peltier cooler, and it just uses air cooling to its minus zero.
I'm sorry, Colin. I'm having a little bit of a hard time hearing your
response.
response.
All right, I'll try it again. The camera is a Peltier cool and uses an air cooling. So it's cooled effectively a fan and reaches a cooling temperature of 0 to be thermally stable.
Okay, thanks. How is the light output of the scintillator related to the X-ray radiation flux?
Well, it's a question for me, I guess. Well, if you have higher flux, you have higher scintillating effect, and there's linear correlation. So the higher flux, the higher scintillating output will be.
Okay. Question here is, how much does the camera cost?
Probably the simplest answer, if you contact Andor, we can give you pricing for your region. It'll be in the currency of the region. So rather than cause confusion by giving numbers out, if you just contact Andor afterwards, we can give you a price.
Okay, great. What is the light collection efficiency of the taper? How does it compare to lens coupling?
Well, it's a good question. and it's about numerical aperture. So the efficiency of fiber optics is higher because the numerical aperture is also higher. For optics, for microscope objectives, you can have aperture about, let's say, 0.5, but for FOP you get a numerical aperture of 1, or almost 1. You can collect basically everything you can get.
Okay, thanks. Let me see here. What would be the theoretical limit of resolution of the system?
Well,
I think. Sorry. The theory is that it's going to be limited by the pixel. Fundamentally, it will be a pixel because well, that's the ideal. So you'll be limited by that. Presently, the optical are the limit or on the edge of the limit. As I think Jerry covered, unless you want to go into slightly more detail, Jerry.
Well, as you said, Colin, it's about the pixel size or the twice of a pixel size. Depends on the definition. But here, the spatial frequency or the highest spatial frequency is the Nyquist frequency, which is at the 0.5 pixel size. So, and also there's some diffraction limit, which is given by Rayleigh criteria, which would be the wavelength over the numerical aperture and some factor of 0.6 or 1, that will give you that the theoretical limit would be below the 1 micron. But because of the sampling frequency is actually lower, it means that the pixel is bigger, and there is 1-to-1 magnification. It will be given by the camera. But on the other hand, we have to say that the limit of imaging in the X-ray imaging that has been achieved is about 0.5 microns. But it's a different concept than the FOP. But on the other hand, with the FOP, you have better light collecting, and there are some advantages of the system.
Okay, thank you so much. I'm afraid that's all the time that we have. I just wanted to thank you, Jerry and Colin, for your terrific presentation, and thank you participants for being a great audience. Be sure to check CNN or CNN Online for information on the next edition of CNN webinars. Thank you On24 for technology and production services, and thank you Andor and Kreider for the sponsorship that made this interactive webcast possible. For CNN webinars, I'm Linda Wang. Goodbye.